thinking that level 3 of fan speed is okay. If it is very cold, then I'm thinking that to stop the fan in 0 level. So if the temperature is low, this one rule. Just see, the rule is if the temperature is low, the fan should be off. First rule. If the temperature is moderate, the fan should be in 3 level. Second rule. If the temperature is more, the fan is in 5 level. Okay. So it is like what? It is according to the certain rules I am giving there. Okay. According to the rule, I am operating the fan. Right. So this is called rule-based technique. In the same way, if I want to if you consider an automated washing machine, okay, this automated washing machine also works according to the rule-based. The best example of rule-based artificial intelligence is fuzzy logic or fuzzy inference systems. Okay, so it forms certain rules. Okay, and if they will compare all these rules together, okay, then accordingly they will take some decision. Okay, so what is that decision? It is according to the rules framed by the user. Just like I'm giving the example in the case of washing machine. Okay, so whenever the clothes are kept inside the washing machine is of load something like 5 to 6 kgs. Okay, then the washing machine will ask you, you just give full cup of detergent. Okay, and the time will be some 70 minutes approximate. Okay, so whenever the load of the clothes are 5 to 6 kgs, it is the rule, it is generated automatically and it is giving you the output. You just give this much detergent and I will take this much time to complete the task. Okay, so that is like rule based. So whenever you are seeing the automated washing machine operation, then it will give you one option just like a fuzzy program. Okay, that fuzzy program is nothing but rule based. It is according, it will be operated according to the rules which are programmed in the automated washing machine. Okay, so these are the three approaches like biological inspired approaches, and the second one is social behavioral based approaches, and third one is rule based approaches. Okay, now I'm giving a specific type and what are those approaches in each category. First, if we see that biological inspired, I already gave the example of neural networks. Okay, in the same way, genetic algorithm, it is also biological inspired. And the third one is artificial immune system, how our immune system works. Okay, and how our immune system it can protect our human body. Okay, so the form of immune system and the working of immune system, human immune system, how it reacts. Okay, it is various numerous algorithms are there, and how those are reaching to their target. Okay, it is according to the swarm decision. If you see ant colony optimization, it is one kind of swarm intelligence. There are group of ants are okay. This birds floating particle swarm optimization. Okay, and if you consider the crab search, how crab is searching its next home. Okay, that is crab search algorithm. In the same way, honeycomb algorithm, where there is a swarm of particles and doing certain searching operation towards maybe the food or maybe the target, whatever it may be. Okay, then it is called swarm based algorithm. Now let us see the case of particle swarm optimization. Okay, so if you see the particle swarm optimization, okay, a particle is nothing but an individual. Here let us consider a group of birds are floating from its source position, maybe from their next, where the next is in which are constructed in trees. Okay, so from trees to whenever they are moving to acquire some food. So now the food position is the target position, that is considered. So source position and target position. Now the group of birds are moving from their source position to the target position. Now what's happening exactly while moving these birds from one position to another position? So here I am considering only one particle. One particle means one bird. Okay, one particle is there. Initially, the particle position is denoted with x. Okay, so initially it is in the x position and it is moving in some direction. Okay, in the direction of v with a velocity of v initially. Okay, now this bird is trying to move. I mean to say this is its own decision. It wants to move its best position, this one. It is thinking that this may be the next best position, so I will move towards this position best, pi position best. Okay, so now this bird, whenever this bird is moving in this direction and is thinking to move in this direction. Okay, so of course its velocity initial position is x and initial velocity is v, but it is thinking that it would be the best position. Okay, then in the group of birds, every particle will have each position best. Okay, so among all these position bests, okay, then they will come to conclude one global best. Okay, so it means that there are, for suppose let us consider there are 50 birds, and those are floating, moving from its source position. So each bird will have their own position first. Okay, then they will communicate each other. The way of communication I will discuss later. Okay, so they will communicate each other and they will come to conclusion that this will be our position, global best. Okay, among all these position best, they will think that this will be our best position. Okay, then the best preferred by swarm is nothing but the global best position. Okay, so there are two best positions. If you see here, one is position best position, and the second one is that global best position. Okay, now all these particles are tending to move towards this global best position, not to their position best position, but they are moving towards the swarm best position. So this particle, if you consider this particle especially, okay, now it is moving in this direction. It is moving towards their position best position initially. Then they thought of this is the global best position. Now the particle is approximating to the best position, which is preferred by the swarm, meant to say towards the global best position. So this is the whole principle of particle swarm optimization. How the birds are moving while communicating each other to gather the food. Okay. So now if we consider this behavior, social behavior of birds flocking, okay, then we can make one intelligence algorithm is artificial intelligence algorithm named with particle swarm optimization. Okay, so I hope all of you understood that. Okay, now let us see how do we implement this algorithm in real time. Okay, so for this case, a position of ith particle. Okay, there are number of particles, but I am considering only ith particle in t cycle. Okay, then the position is x and v of ith particle in tth iteration. Okay, now the velocity and the position will be updated according to these numbers. this is the empirical relation which was developed by the scientist who developed this algorithm. Okay, so the simple principle is that initially VTI plus 1 should be, just omit some weights here. I will tell you why these weights are required. Okay, so it's initial velocity plus some component into the position with respect to its position best, and some component into its position according to its global best. Okay, so here the velocity, what I am saying is that it is not meter per second or centimeter per second. It is also a position shift. The parameter here, the velocity we are considering, it is the next position shift. Okay, now it is not the meter per second. It is also a position value, position best. Okay, so the position shift. Okay, the position shift is updated with respect to this VIT plus 1, which is a function of its local best position and global best position. Okay, now coming to the solution that, okay, so in order to exactly, for suppose there are number of particles are there. Okay, so if certain weightage for each parameter is not, for each particle is not considered, then what will happen? Whenever these particles or birds are moving, there is a chance of collision, because only one global best is there. Okay, everyone is trying towards that global best position. So when every particle is moving towards the global best position, what will happen? There will be a chance of collision. Okay, if there is collision happens or colliding each other, again it is the worst situation. So in order to avoid the uncertainties or irregularities, okay, so these parameters are added. Okay, so these parameters then will be tuned in order to avoid those uncertainties. Okay, so the weightage, this W may be given as 1 or 0 in between 0 and 1, or 1 between 0 and 1. Okay, but it must not be 0, should not be 0. Okay, and here this C1 and C2 is nothing but the cognitive parameters. Cognitive parameters means, I mean to say that to avoid the collision. Okay, I mean to say some kind of intelligence should be there. So those parameters, cognitive parameters, we can say this C1 and C2 are cognitive parameters. Of course, we can say these are the social parameters also, C1 and C2, and these here random, that is, say here random. So these random parameters are random parameters which may be considered or may not be considered. For suppose if the problem is too much complicated, okay, then we have to use this parameter which can be varied from 0 and 1. Okay, if the problem is so simple, then simply we can say these random values as 1. Okay, so now from this figure, what we got is that VIT plus 1, I mean say the next position shift will be this one, and according to this position shift, the position will be changed. XIT plus 1 is equal to XIT plus VIT plus 1. So for the T plus 1th iteration, the particle should go to this position, right? Hope it is clear. Okay, so this is the mathematical equation of particle swarm optimization. Now let us implement this particle swarm optimization to the mobile robot navigation. How a mobile robot navigation and how we can implement this particle swarm optimization for a mobile robot to navigate within some kind of environment. So, first of all, see, here if you see the first point, initially the mobile robot is going towards the goal within its unknown environments until it has to be faced objects or obstacles in front of it. Just like this, a simple example. Okay, consider a manufacturing plant is there. Okay. So in the manufacturing plant, I want to transfer certain goods from one manufacturing unit to another manufacturing unit, or one work cell to another work cell. Okay, so I am using one mobile robot automated guided vehicle here to move from one manufacturing cell to another manufacturing cell. Okay. So obviously the used automated guided vehicle will move from one position to another position if there are no disturbance, no obstacles, no uncertainty. That is obvious. Now the problem is that in the environment, any kind of disturbance or uncertainty is there, then the robot has for the next moment of the robot in order to reach the target. So here what my point is that of course this is developed by me, okay, and how I developed the algorithm is that, okay. So here this a robot is free to move towards the target position. If the robot is sensing some obstacles, then this developed particle swarm optimization based motion planner will be activated. How this is activated, let's see. So, in order to do the communication, just in the previous slide I said that there is communication among the swarm. Okay, so what is that communication and how the communication happens? Let us see. Okay, so in the case of robot motion, the robot should follow these three optimal criteria. The optimal criteria are like this. The distance between the robot and the target should be low, obviously. So my first aim is to move the robot, okay, which follows the shortest distance to reach its target. Okay. Then the second objective is that the distance between the robot and the nearest obstacles should be, of course, for some 10 number of objects. At a time 10 number of objects is sensed. But among these 10 number of objects, which it has to detect initially move of course the robot should move towards the target. Okay, so these two optimal criteria, and the third one is that the total distance traveled by the robot or time traversal should be low. Of course, whenever the robot is following these two, then the third objective will happen. The robot should move with less time, okay, to reach its target. Now, how do I, so based on these three objects, how do I communicate to my robot to move towards the target within less time? Okay, now I'm looking off this flow diagram, how my robot is being performed, its mobility operation in unknown environment. Okay, now the program is started. I mean to say that my algorithm is started. Okay, now the robot is moved towards the target, towards the goal, towards its target. Okay, and if there are some objects presented in the environment within the sensing region of the robot, then this PSO will be activated. Okay, if there is no objects presented in the environment, then simply the robot will move towards the goal. Okay, then it will go to the towards the target. It will be finished easily. Okay, if the goal is reached, okay, yes, it is stopped. Your task is completed. If it is not, move the robot towards its goal. Okay, so this is one criteria. If there are no objects, here the problem comes here. If my robot has sensed some objects, okay, then the particle swarm optimization will be activated. So that is what is going on. That initially some population I am considering, okay, So whenever this population considered, this should be within the sensed region, robot sensing region. I will explain in the next slide, then you will have a clear idea. Okay, so initially I am generating some population. Okay, for this population I am giving certain positions and their velocities. Now the point is that each individual particle will have their position best values, already I discussed. Okay, then after this communication, which particle is near to the target, which particle is away from the object. Okay, so according to those two criteria, then I will go for the global best. Okay, I will go for the global best. Then the global best, then according to the global best, I will update the position and the velocity of each and every particle according to the previous equations. Then once the global best is found, then the robot will move towards the global best position. So now the robot is moving to the next best position. Okay, then it will check for whether my target is reached or not. Okay, so here the robot reached its target, then it's fine, it will be stopped. If the robot is not reached, then again another group of particles will be generated and the operation of these three steps will be continued until it reaches its target. This is the flow diagram of the working of the developed PDS of this motion planner. Okay, now the point is that here if you see, okay, this is my work environment. Okay, so in this work environment, initially an environment is with only one object. Okay, this is source position. The robot knows this is I, and this is my target position. I should reach. Okay, now since the robot knows this is my target position, it is moving towards the target. Okay, so the robot position is here represented with green colored dots. Okay, now the robot is moving towards the target. Okay, so until some objects are formed. Okay, now the robot reaches to until some object sensed within its sensing region. So now if you see here, the robot has sensed some objects. Since the objects are presented, the robot is thinking that where shall I go? Okay, then here the particle swarm optimization will be activated. So in order to activate that particle swarm optimization, initially I am generating some population within the sensing region. So this is the sensing region of the robot, and among within this sensing region, around 80 number of particles are being generated with initialization of its position and velocities. Okay, then each particle here saying that it is their own position best. Okay, and it will be all these particles will be checked for those three objects what we mentioned. One is which particle is nearer to the target and which particle is away from the nearest obstacle. Okay, once it is decided, then somewhere here is the algorithm found this would be the best position. Okay, now the robot start moving towards the global best position, which is detected by this particle swarm optimization algorithm. So this is initial robot motion towards the goal, and this is when the swarm is generated by the robot when some objects are sensed. Okay, so now if we see here in this third scenario, okay, in the third scenario, what's happening? There are some 1, 2, 3, 4, 5, 6, 8, 9 objects are presented in this manufacturing units. Okay, now my robot is moving from its source position to the goal position. Okay, then it will think what would be the best position. So excuse me. So what's happening? The green color path, if you see here, there are three colors in the path. One is green, Okay, second one is white color. Okay, and in between you can see some red dots. Okay, here also red dots. Okay. So here if you see at the source position, the robot started at its source position and moving towards the goal. Okay, then this white path is representing the PSO generated path, means particle swarm of a generated path. Okay, now it is generated. Okay, then again it is finding that there are no objects. Then it is green path, again white path, again some green path. Okay, so while following these paths, if we observe, there are number of paths are there. Okay, and of course each path is moving towards the goal. But among these, see, if you clearly observe here, there is object collision, and here also some parts are given object collision. Okay, and here also some object given object collision. So we should filter which paths are those, and we should properly tune the values where we are getting the non-collision or collide-free path by the robot. So these many paths are generated whenever I am changing the values of C1 and C2. At that I said that these C1 and C2 are cognitive parameter, are social behavior parameters. Okay, na? So while changing these C1 and C2, I am getting so many paths. So at which C1 and C2 the collision happens, those paths, those values I should not consider. Okay. So this is one case. And in the second case, here in the fourth scenario, the environment I changed. See, all are collision free paths. Okay, I mean to say here I tuned the values of C1 and C2. I optimally maintained at one C1 and C2. All these are collision free paths. But the this behavior of giving number of paths while running each time, the behavior is called stochastic in nature. Why it has happened? See, if you see the second figure, okay, here the random population generated is in this way for the first time. If I run this algorithm for the second time, this may vary. The random generation may vary. Okay, thereby there will be the change in its population is different. Here, that random what is that the I'm getting the right path or not. Second thing is that the shortest path to the the path traveled for these 20 runs should be within 5% of threshold. Of course, the developed algorithm is also Hello. Sir, is it audible? Sir, is it audible?
Yes, sir, is it audible, but screen is blurring, sir.
Yeah. I'm going to full screen. Now it is okay, na?
Now it is okay.
Okay, sir. Thank you. So this is the stochastic nature, and we have to avoid. Of course, we have to reduce the stochastic nature by running the algorithm for at least for 10 times. Here I run the algorithm for 20 times. So now let us see by video how this algorithm works. Okay. Now. So initially one particle it is considered, okay, and its velocity it is there, okay. It is considered it is its position best value, and it is decided some global best value, okay. Now the particle is approaching towards the global best position. Now I am applying this strategy to the robot motion, the simulation environment, okay. Now if I see this one, the robot is initially started here, and here this is the target. Let us consider this is the manufacturing environment, okay, which has certain objects over here. 5 objects are there. Now the robot has started its motion, okay, and it is moving towards the target, okay, because it has not sensed any objects, right? Okay. Now the robot has sensed some objects, okay. How the swarm is to be generated within its sensing range. Let us see. If you see this one, okay. So here when the robot is moving one by one, okay, all these are robot sensed objects, so that at each interval, each iteration, the robot is generating some swarm, and it is deciding its path, okay. That white color path is the PSO generated path. Now let us see here how it is moving. Okay, so this red one is showing the global best position, and towards this red object the path is moving. So this is the swarm, and swarm based position best values, global best values, and moving towards the target values. Okay, so without the swarm, okay, the same path only without the swarm, how it appears. Okay, just moving towards the global best position, no object presented here. Okay, again white path is PSO path, okay, again white path is PSO path, and moving towards the target. Okay, so this is another environment, and how the PSO is generating path, okay, and how it is moving white path, and in global best positions, okay, and how the robot is moving within the environment. So this is without swarm, how the robot is moving. Right, this is so this is the first case of swarm intelligence algorithm, which is social behavior based algorithm, which the motion planner gives the optimal path to move the robot towards the target. Okay, next algorithm we'll focus on artificial immune system. Okay. So, what is this artificial immune system? Let us have a look on this. Okay. So, if you see this artificial immune system, okay, just I am giving an example of our human immune system. So, if we consider our human immune system, what happens? Whenever our human body or immune system reacts with some sort of antigens like bacteria or virus, then our human system, immune system, or human body tries to fight with those antigens like bacteria or virus. Okay, so whenever our immune system produces some protective cells to fight with this bacteria and virus, then we say that our immune is good. For suppose, some human immune system is there, okay, is suffering with fever, then the specific immune system will generate the antibodies which can reduce the fever. Okay, so it produces especially those antibodies which can fight for the antigens of fever. If someone is suffering from cold, then the human immune system will generate the antibodies which can fight with the cold related bacteria or virus. Okay, so there are a number of antigens which may cause various effects, maybe cold, cough, fever, whatever it may be. Okay, na? So whenever these bacteria or virus are influencing the human body, our immune system reacts to those virus or bacteria. Okay, na? And it generates antibodies specific to the each and every type of antigen. For suppose one immune system is like this, an immune system is producing fever-related antibodies, but he is suffering from cold. Then we can say the immune system is not good, right? Okay, so the immune system should be like this. Okay, if for the first time, if the antigen, for suppose, if a person is suffering from cold for the first time, then randomly the antibodies will be produced. Okay, whether these antibodies are neutralizing the antigens which are related to cold or not, it will check repeatedly, and if it is not neutralized, another antibody will be formed. In the same, if it is not neutralized, again another type of antibody will be formed. Okay, so once it finds the immune system finds a suitable antibody, then it will be in its memory. So this is the cold type antigen. Now I will say this: if next time the same virus come to the body, then I will produce this kind of antibody. Got it? I believe. So in this way, our human system reacts with antigens like bacteria and virus. Okay, so these antibodies or protective cells are producing by the human system. It is called B cell to these antibodies, and these antibodies will be reacted to the antigens. Now let us see this immune behavior. If we develop some sort of intelligence and if we apply this intelligence to any sort of case, then we can say that is the application of artificial immune system. Okay, so how this can be applied to the mobile robot navigation to generate an efficient mobile robot navigation. Let us see. So initially here the immune system of the body consists of B cell. Okay, this is B cell. Okay, so the B cell here, we are considering as the robot, our intelligent robot. Okay, now B cell produces what? B cell produces some protective cells, nothing but antibodies. Okay, in the meanwhile, our intelligent robot, mobile robot, it will produce what it can produce, some possible robotic actions, either move left, move right, move straight, as like this. Okay, so it is producing some possible robotic actions. Okay, now these antibodies will be reacted with what? Antigens. Okay, now so these antigens, how these antigens are and what type of antibody is suitable in order to neutralize this antigen, it will take care of. In the same way, among these robotic actions, which robot action to be performed, it will be interacted with environment. Okay, and for this environment, what is the suitable robotic action? It will be taken decision by our intelligent mobile robot. This system is called behavior learning. Okay, and here it is called immune response. So if you see the similarities between this immune system, a mobile robot navigation can be inspired or mimic towards the immune system. So this is called immune-based motion control strategy for mobile robot. Okay. So what are the possible robotic actions I am considering here? It is considered only 5 robotic actions. Those are 90 degrees motion, 45 degrees motion, 0 degrees motion, either in reverse of 0 degrees and 90 degrees reverse. Okay. So if it is in the first quadrant, I mean the robot is moving towards these 5. If the robot is moving towards left top corner, I mean say the second quadrant, these are the 5 robotic actions. If the robot is moving in the third quadrant, then these 5 will be the antibodies, and if the robot is moving in the fourth quadrant, then these 5 will be the robotic actions or antibodies. So there are total 5 into 4. 20 possible robotic actions is being considered here. Okay, so among these 20 robotic actions, okay, the robot will take care which robotic action is suitable towards the towards the sensed environmental criteria. So this is the situation where the robotic mobile robot navigation can move towards the environment to reach its target, okay, whether it may be in the first quadrant or second quadrant or third quadrant or fourth quadrant. Okay. So here I am not discussed about how the behavior-based learning is possible here, because it is the mathematical complexity is there and it will take around 1 hour to explain all this. So I have not considered what is the behavior learning here, but I will show you the results of how the results are produced while following this immune system. Okay. So here what I did is that I consider 2 environments for the better understanding